Welcome back, everyone. We're working with fluxes, and this is Calculus 3. We're in 15.6. I'm going to give you another example. In the last one, we just used the normal vector or the normal formula f dot n ds, the integral of that. And we're going to stick with that. But if we're using a standard area where the surface, where we have like a surface z as a function of x and y, this also works with y as a function of x and z, or x as a function of y and z, but the one we're most familiar with is the z as a function of x and y. We're going to assume positive orientation is in the direction of z. So I could write g as z minus the value z minus z as the function of x, y. And we take the derivative, we get negative, we get this formula right here. And we've seen this before when we did cross products for RU and cross RV. When we looked at this, we did in 15.5, and I think we've done it before that too. So if I call G that Z minus Z as a function of X or Y, we can rewrite this RU cross RV is just the gradient of G. When we took the gradient of G. So rather than doing f dot n ds, we just have f dotted with the gradient of G, du dv. And since uv is in the xy plane, that's just what ends up being what we're going to have. So uv is the generic form. It's whatever letters we're projecting into. It's those letters. Okay. So if you're doing z, it's going to go into dx dy. If you're doing x, it's going to go into dy dz, etc. Let's look at an example. We're going to find the flux where f is y in the x direction, x in the y direction, and z in the z direction. And S is a closed surface bounded above by the paraboloid z equals 1 minus x squared minus y squared, and below by z equals 0. So we got some kind of cone and the bottom of the cone. Okay. So there's two surfaces to consider, the one on the bottom and the paraboloid. Both of these are z as a function of x and y. The top one, we already see what z is, the function of x or y. The bottom one, z is 0. It's still a function of x or y, but there's no actual component there. Let's look at our solution. We're going to do this up here. We're going to do the gradient of g, and we're going to dot that with our f, and we're going to go from there. So it is kind of weird looking at how it's going to look with y and x. So in the x direction, it goes in the y direction. But the normal is pointed outwards. So these are the arrows for the normal. Sorry, that's not the arrows of the force. So in the x direction, it's pointed in the y direction. And in the y direction, it's pointed in the x direction. It's kind of crazy. All right, let's take a look at it. So we got our formulas again. All right, we're looking at the first surface, the paraboloid. If we take the gradient of that, we can look at it two ways of really getting it. We solve for g, and we get everything over on the left. We got 2x, 2y, and 1 when we take the gradient. Or we can use this one up here and just take the partial both times, find out what z is with respect to x, z is with respect to y, and just plug them in to our gradient of g. Both approaches get you 2x, 2y, and 1. Okay. I might show that a little clearer. When we do derivative z with respect to x, we get negative 2x. And remember, what goes in for del g is negative zx, negative zy, and 1. So if I'm going to do negative of negative 2x, I get the positive 2x. Okay. Negative signs are the quickest thing that throws students off, and I don't want to rush that part. All right. So I set up my f dot g, and I get 2xy plus 2xy plus 1 minus x squared minus y squared. The projection is into the xy plane. The paraboloid looks like a circle in the xy plane. So maybe we should switch to polar, do stuff in polar. I combine 2x and the 2xy's together to get 4xy. Remember, x is r cosine theta, y is r sine theta. And then we have negative x squared minus y squared ends up being negative r squared. Don't forget your conversion factor, your correction factor when you switch to dr and d theta for polar. Our radius was 1 in the unit circle. So we go through and we substitute in, work it out. It's not really separable because we've got pluses and minuses in there unless we make a bunch of different integrals. So I just went through and did it as 1, and I got pi over 2 for the top surface. The bottom surface, if we did, I actually wrote out the f dot n ds to show that it's negative z ds. Because it's important that we see that. But in your head, you know that the normal is pointed straight down. So if you think about it, if you know the normal is straight down or straight up, you know the normal is only either -1 or +1. Okay? So all of our field goes in that direction, but z is 0 there. So when I put in 0 here, I've got the integral of 0. So the surface 2 is 0. We can add the two surfaces together and we get pi over 2. That's it for this video. I got one more video to talk about flux. Peace. We'll do more problems in class.